Yeah.
Yes, yes. Hello, everybody. We are finally live for the session on quantum machine learning. Trust me, this is one of the key technologies that is required in order to survive in the future. Not just dealing with quantum bits or the bits of ones and zeros. It's all beyond it. The potential of quantum machine learning is yet to be known, and we are yet to solve a lot of mysteries behind it. So right now, this is Azure Developer Community Bengaluru chapter. I'm the organizer there, and I organize a lot of events there on different things like what different things like cloud, AI, and things like that. But I always make sure that there are different topics done. So this is where we actually learn something new beyond what we can reach. So right now, our community just focus on learning, growing together, upskilling the community, and just it gives me a chance to learn something new also. So, in this section of upcoming events, you can get to know all the upcoming events that are coming up, and you can also get to know, okay, this is what is happening in our community. And if you want to be an organizer, go ahead and click on this entire thing of all the communities, join it, come contact us, or organize the events, be a speaker, and things like that. So, there are some past events, just go through them, and also these are the set of organizers. It's me and Vivek Raja and everybody here, and speaker bureau is here. Do register here. So yes, that's it from my side, and thank you so much, folks. This is Priyanka Sharma. Trust me, she's one of the most humble human being that I met. And right now we are telling ourselves how to learn quantum machine learning through her. And thank you so much, ma'am, for giving this webinar.
No problem. It's my pleasure.
Yes, ma'am. Sure. I'll move out of the screen. You have shared your screen, right?
Yeah, I'm already sharing my screen.
Sure, ma'am.
Yeah, okay. Yeah, so you need to put it, yeah, screen share view. All right. Yeah, so I just, Vishwas, just let me know, we don't have the same problem I was having earlier, right? So, okay, so this one is, yeah, is it
This
okay
is
now?
perfect. Yes, ma'am.
All right. So, yeah. So maybe should I start, or you need to wait a couple of minutes, or what?
No, no. You can start, ma'am. You can start.
All right. So, hey Vishwas, so thank you for having me on your forum. And I saw the list of topics which are lined up pretty interesting. And I saw that you yourself are going to speak on Azure functions and Java. So, quite cool, cool topics, Azure functions. All right. So, yeah, having said that, all the best, Vishwas, for all your organizing efforts. And yeah, I would like to feature in the future, let's say for AI series or cognitive series and stuff. All right. So yeah, good evening everybody who's joining, and trust me, this is going to be a quite interesting journey today with Azure quantum computing. So I myself am quite a newbie to this technology. So I really just attended a couple of workshops which have been released by Microsoft Azure and the quantum computing libraries which they have released, right? But as I read more about the basics of quantum computing, like quantum computing comes from quantum mechanics, quantum physics, right? And I was like literally blown by the basics, the fundamentals that go into laying the foundations of quantum computing. All right, so I'm sure that throughout the session today you all are going to have as much fun as I did when I was unearthing the beauty of quantum computing. Okay, so quickly, without further ado, this is about me. I'm the Microsoft MVP for AI, and also the analytics, which is data and AI lead currently in my organization. So I work for Avanade, and if you want to connect with me, you can always do so on my Twitter handle at Fuzzy Mindman. So you find a lot of interesting things going on over there, where we share medium articles towards data science blogs and stuff like that. Okay, so yeah, before we go to quantum mechanics, right, we need to look at a very interesting quote which comes from one of the key persons who gave us the idea behind the quantum computer, right? So there were a lot of pre-runners and precursors to Richard Feynman. So Richard Feynman is a very noted name in physics, right? So he was a theoretical physicist, if I'm not wrong. And yeah, so one of the very notable names and respected names in the world of modern physics, especially, right? So when you talk of quantum mechanics, what he said, and which actually fits the paradigm of our nature, like nature around us, and not the nature which we see, like not the macro level. We go down to the subatomic particle level. So for that, it holds very true what he said. So he's saying that nature isn't classical, and if you want to make a simulation of nature, you would better make it quantum mechanical. And it's a wonderful problem because it doesn't look so easy. So obviously, like when you want to do some simulation of nature at the quantum level, which is at the particle level, atomic particle level, it's absolutely not so easy. And why it's not so easy is something which we will delve into right now. All right. So what is the motivation and behind this the entire branch of quantum physics, quantum mechanics, quantum mathematics, and then quantum computing? So quantum computing rests on the robust shoulders of all these pillars. So we had physics, we had computations on top of that, so there was a mathematical base. So you have quantum chemistry, you have the principles of chemistry coming into play here, especially Heisenberg's uncertainty principle. So people who have just been through their 12th standard exams, or have are majoring in PCMB and all, will immediately recollect. So all these principles beautifully coming together, even Schrodinger's cat for that matter, and how Schrodinger's cat fits into our quantum computing paradigm is something which we'll touch upon subsequently. All right. So when we talk of the motivation and the basics of quantum computing, so Richard Feynman was the one who proposed an initial quantum computer, right? And quantum computer will always come with quantum circuits. Okay. So basically, like if you look at our classical computer, which has your normal registers and logic gates, right? So you have AND or XOR, all those logic gates are there, and bits are there, computational bits are there. So same way, and all these are operated upon by transformers connected together and stuff like that. So in the world of quantum computing, we have quantum circuits. Okay. So quantum computing is a new paradigm which extends the basics of quantum mechanics to the world of traditional computing, right? So actually, you take your traditional problems, like the normal problems or the algorithms which are currently being solved by your normal computers, the classical computers, and then they want it to extend to the they want to apply the basics of quantum mechanics to that, to maybe discover newer problem areas which we could solve, or the current problems, make them solve exponentially fast. Okay. So quantum systems which Feynman wished to simulate could not be modeled by even a massively parallel classical computer. So what happens is, if you just keep on adding computing power, right? So for example, like you have a 64-bit your RAM size usage, you have 64, or 256 and stuff like that. Even in case of AI algorithms, if you see, you have CPUs and you have GPUs, and but just adding computing power is not going to make your algorithm efficient. So when I talk of efficiency, I'm not only talking in terms of the time taken, right? So for example, if you were to have a deep blue sort of an algorithm which used a brute force method to beat Gary Kasparov in chess, right? So in that case, you just keep on adding resources. So the even though the time taken is going to reduce, the hardware, the software cost, and all others are will keep on increasing, right? The amount of computing power which you cram into that, right? So that doesn't make your algorithm efficient. Efficient is not only like cramming in computational power and more hardware and more circuits and stuff like that, but it is also achieving that in an optimal set of resources, optimal infrastructure. So how to do that? So, like there are many problems in today's world which if a normal computer, if it were to solve, it would take it like hundreds of thousands of years, even with the massive level of computational power and resources which we have with us right now, right? So that is where, quantum systems pitch in, and the qubits, which we will talk of shortly, they come in handy. And whatever, was to be solved in, let's say, like 5 years, can be solved in 5 seconds with the help of quantum system. So if classical computers, even though you are, talk about your parallel processing and geographically distributed, and talk of farms or clusters and all those things, right? So even with all your scalability and spark parallel computing and all of those things, also with classical computers, with regards to certain problems, there are certain limitations. And let's say if a problem can be solved by a classical computer in 5 years, a quantum computer can solve that problem in 5 seconds, right? 5 minutes, 5 seconds, whatever that is, depending on the way we organize our algorithms and our resources, right? Again, just, to go back to that, there are problems which classical computers can solve, and quantum computers can never be able to solve. So going forward, like in the future, if you look at a futuristic point of view, that will be like, quantum computing and classical computing working together in tandem to extract the best of each other. All right. So yeah, so Richard Feynman was the one who who laid down the proposition for a quantum computer, right? And of course, it was built upon the work of a lot of other notable scientists. Max Planck was there, Einstein was there, and Heisenberg was there, right?
Ma'am, are you still in the motivation and introduction?
No, I already. No, no.
Oh, okay,
Yeah,
okay.
yeah, yeah. Now I change the slide. Yeah,
Okay,
yeah,
okay.
yeah. I'm still in the motivation. Yeah, right.
Because the
So this
concept was
is,
somewhere and the slide was.
yeah. No, I was still on the motivation only. I was talking on all these three paradigms only. So yeah, I'd not moved on, right? And yeah, so this is, just a still of Richard Feynman. He's laying down the basics and explaining the basics of quantum mechanics at CERN. So CERN, as we all know, is a Large Hadron Collider, right? I mean, for simulating the Higgs boson particle and all the modern physics jargons, So yeah, forgive me because I'm not a physics student, right? So yeah, so just a short, anecdote here. Okay. So now, so pardon me for the title, Rise of the Quantum Machines, right? It has a bit of plagiaristic undertones to it. Anyways, so when we talk of the quantum machines, right? Now, let's say if you have, a bit, okay, in our normal computing structure, right? So, Vishwas, just correct me. I'm on the correct slide, right? Rise of quantum machines. You're able to see the same thing at your side, right?
Yes, ma'am. Yes, yes.
All right. Okay. So now when you look at quantum machines, okay, so just think, just take a moment to think about this, and why we have such exponential speeds at which quantum computers can operate, right? So uh, when you talk of a bit in our reality world, which we say the normal world, the normal physical world, or the normal classical computers which we use, it has a value 0 or 1. So let's say when you flip a coin, I know that it is either going to be heads or tails. Okay, so you I denote heads as 0 and something as 1. Or even for a classification problem, so let's say I have roses, daisies, and tulips, right? So then I bring another flower. It can be either of those three or none of those three, right? So it can't be a rose and a daisy all at once, okay? Or I can't have a heads out all or tails all at once, right? But whatever the laws of physics which we see are applicable at our normal macro level, right? We as human beings, we perceive certain things, and we perceive certain things as reality. Like, I am at point A, I cannot be at point B all at the same time, right? I mean, I need to have some sort of duality to exist at both places at once, right? So these are the normal laws of physics which govern us, which govern the things around us, okay? But when you go to atomic levels, these laws don't hold true. I mean, all of our notions of reality and causality and cause and effect are totally shattered, okay? And why is that? So okay, so if we have two electrons, so when you go to the atomic level, okay, particle physics, when we talk of that, right? So that time it is all electrons and the spin of the electrons and photons and positrons and all those particles they're out there, right, with all their fancy names. Okay, so when if we have two electrons which can be at 2 points, so A and B, okay, so it's like your heads or tails or 0 or 1, right? Then there could be a possibility that it can be both 0 0, like it can be at point AA, it can be at point BB, and it can be at point AB and BA at the same time, right? So with two with the two possibilities, like with the two this thing bits, you have 2 raised to 2 possibilities. With 3 electrons, you can have 2 raised to 3 possibilities. So with 10 electrons, you will have 2 raised to 10 possibilities. With 20 electrons, you will have more than a million probabilities, right? Probabilities, right? And so what happens is the measurements, they quickly go out of hand, because as you see, the calculations are not linear. So let's say if my 64 GB RAM is able to solve a problem in 5 minutes, and then I add another 64 GB RAM, then logically, like, because the memory is doubling, the time would be linearly reduced, right? So same way, like if you keep on adding more cores and more CPUs and more clusters and more nodes and all, it's a linear increase or decrease which you see. It's a linear relation. Here it's an exponential relation. So for 3 electrons, if you see, because of the case that it can be here and there at the same time. So these states, right, these states in which the electron has the probability of being at two places at one time, okay, which is also called as a wave particle duality. We'll come to that, right? So yeah, because of these sort of thing, which is again, as I said, very hard to sort of digest, right? So I mean, how can I be at here and there also? So sort of shatters all our notions of realism and whatever we are seeing. So that is why we say that when at the particle level, at the atomic level, all these our normal physics laws, they don't hold good, right? So which means an electron having all these sort of probabilities, right, which is what makes the computation go out of hand very quickly, which is what our normal classical computers cannot handle, right? So that is why when Richard Feynman suggested that you have quantum circuits which can control these state of electrons, right? So which is something like an in between state. So imagine that you are flipping a coin, right? So now when you're flipping a coin high up in the air, it when it finally lands on the ground, that time you will see that okay, it is either a heads or a tail, right? But when it is in midair, when it is being in the transition state, in the transition state it is both a 0 and a 1. I mean, so that transition states which are there in between, that is something what we are calling as the intermediate states here. Like it can be at point A B at the same time, or it can be at the point B B at the both A and B, or B and A, and stuff like that. Okay, so this is why quantum computers that harness these properties of the electrons and their wave particle duality and the state vectors and other entanglement properties and all. So because of this, the quantum circuits which harness these capabilities, that is why they are able to solve problems exponentially better. But then again, there are certain limitations to what sort of problems these quantum computers can solve, right? Okay, so we've talked a lot of quantum. So what is a quantum? Okay, quantum is a term which essentially comes from quantum mechanics, of course, right? Which is again, like if people who are doing classical physics, so they will study Newtonian physics, and then they will study other for example, I mean, from Newtonian and classical physics they will move on to modern physics. So they will move to Max Planck, and they'll move to Einstein physics, and then you come to modern physics, which is what we call as particle physics. Quantum mechanics is a branch of modern physics, right? And it is a field of physics which tackles the physical properties at an atomic scale. So like the atoms, and which is then subdivided into the electrons, protons, photons, and I mean neutrons. And then you have the CERN hadron collider, which is trying to simulate this Higgs boson particles and stuff like that, right? So what I was talking of, so at the particle levels, the physics rules, they cease to apply, the normal physics rule which we see, right? And because why? Because of the wave particle duality, which means the objects, they can function both as waves and particles. Okay, so imagine, like, you have a three-dimensional space here, xyz, what we see objects in three dimensions. Now if I were to plot a point, okay, if I were to plot a point, and that point could be like a coordinate like 111, okay, or xyz. That is how I plot a point. And then if you go to a bit of mathematics side, then you have the imaginary scale where you have the complex numbers and stuff like that, right? But just for real world cases, if you see that xyz is how you will denote a location of a point in the coordinate system, the three-dimensional coordinate system. Okay, but what happens if an electron can be a wave and a particle at the same time? All right, so how do you denote of the position or the location, or how do you represent such an electron? I mean, what sort of representation you use for that? So this is given by something called as Hilbert space. Okay, so I don't know, people who are working in computer vision, for example, will be familiar with the paradigm of eigenvalues and eigenvectors, right? So which means I mean, in eigenvalues and eigenvectors, when you go there, so it is like the spin of the electron. Okay, so the space in which your point is located, and the amount by which it is stretched and stuff like that. So same way, if you were to represent an electron in this quantum, okay, so in this Hilbert scale, okay, I will just go to here, so that I'll come back to the slide later on. So when you go to this Hilbert space, okay, when you go to this Hilbert space, when you're trying to represent an electron, it will be the spin of the electron, okay, and because the electron can be a wave and the particle at the same time, right? So it can be the spin, it is also the orientation of the wave, and then at any point of time, to denote a point, it will be a complex wave function. So it is no longer a simple xyz sort of a coordinate space. You imagine, because it is a wave particle duality, right? So you will have a complex wave function at any point of time to denote the exact state of that electron, right? So that electron is in what state, so what is the position, what is the orientation, and all of those things, right? So this is the Hilbert space, which is used to represent quantum points. Don't stress yourself too much about it, because we are this is not a physics or a it is not a quantum mechanics session. Just to put things in perspective, right? And how when we are talking of quantum spaces, all the representation also changes, right? So you don't have your normal xyz geometric space, so you have a Hilbert space, and this is how at any given point of time the position will be a complex wave function. Okay, because I mean, the electron, if you the electron could be a wave and a particle at the same time. Okay, and it could be at A and B at the same time as well. So, yeah, so when we were talking of coming back to the previous slide, so wave particle duality. So, object functions as both waves and particles, right? So, in quantum environment, if I knew a certain sort of prerequisites, right, and a certain knowns are there beforehand, then I can predict its state in the future, right? So, given set of known initial conditions, I can predict something in the future. So that is what is a wave function, right? So given this knowns, given this sort of variables, known variables at this point of time, at n point of time, at n+1, if I apply the wave function, I can predict some sort of information about what it will be at n+1. Right, so this is Heisenberg's uncertainty principle. Chemistry guys, give a shout out if you can relate to this. Okay, and this is from where, I mean, combining all these principles, this is the four pillars of quantum computing which you get, which is quantization, entanglement, principle of uncertainty, and wave particle duality. All right, and because we keep on saying that every time we need to keep a track of the states, right? So the complex wave function which you have, the complex wave function of each a point in time in the Hilbert space which you have, it is nothing but the state vectors, right? So something which has a spin, which has a direction, which has a orientation. So it is a nothing but a state vector. At x point of time, what is the state that particular electron or the wave particle is in, right? Okay, I won't go into eigenvalues and eigenvectors, right? So because it is going to put a lot of physics and mathematics unnecessarily, because this is not what we are set out to do. We don't have to actually view some Hilbert space or prove ourselves to be the tenets of quantum computing, right? So we are just here to see the beauty of quantum computing, the basics, very basics, and then we jump on to how we can bring it into our day to day and use the efforts which IBM, Google, Microsoft is putting by leveraging their libraries. All right. Okay, coming back to the wave particle duality, which I was talking of, very beautiful diagram here, right? So this is the electron particle position. At the same time, it can be the electron wave momentum, right? Because of which, at any given point of time, you can just make certain assumptions or probability calculations of the state that particular particle will be in, right? So it is all about when you talk of functions, like given x, what is f of x, right? So given x, what is y is a function of x, f of x is a complex wave function. And you can never be certain for, I mean, you can never be certain that, okay, at this point of time, this is the state of that particle, right? So you'll always be probabilistic, as what your machine learning and AI is all about. You're just dishing out probabilities and say probably I mean, given this forecast or given this past data, probably my forecast for the next 10 years is so and so. And then you calculate the accuracy and all other things, right? Given the function which you have, your machine learning algorithm has derived. So same way, quantum mechanics is all about measurements, possible measurements. Okay. So the state of a given system is described by a complex wave function, because as I said, like, you cannot have a discrete XYZ sort of a system because of the wave particle duality concept, right? So you can only measure the probabilities of the results. So when I'm flipping the coin, okay, so of course flipping the coin is not a quantum computing problem at all, right? I'm just telling that the in between states of the coin which are there. So at like let's say I flipped a coin at time x, and at time x plus 4 it fell down. So in x plus 1, x plus 2, x plus 3, I can just make some assumptions about the probability calculations about the states of what that coin was in, right? Given the complex wave function which I'm computing based on certain initial knowns beforehand, right? So this is that is why it is called as probabilistic. So at any given point of time, we can only measure the probabilities. Okay. For example, we could measure the probability of electron being in X region of the electron cloud. All right. So yeah, so all of those you will see, like even the algorithms which we will be seeing in our demo, right? They will be all about probability calculation. So you will have computations like H computation, M computation. So H is and we will come to that shortly. I don't want to spoil all the fun here. Okay. Now we have talked so much about quantum mechanics and quantum physics and the wave particle duality function and stuff like that. Okay. So what are quantum computers, right? So when we come to quantum computers, okay, so go back to the very first slide which we had, right? So I'm already on the 10th slide. Yeah, here, right? So this is not just all, like, I mean, initially it looks like a picture of a drill or something weird like that, but this is what a quantum computer looks like, right? So I mean, if you look at so these these are all comprised of quantum circuits, right? These are comprised of quantum gates, quantum registers, and quantum gates are like, very I'll show you some calculations involving quantum gates. So like we have your or and NAND XOR gates and stuff like that. They have polys X, poly Y, poly Z gates and stuff like that. Very, very, very interesting, very funny also. Okay, we'll see that in our algorithms. Okay. Yeah, so we are talking of what are quantum computers. So now quantum computers are the machines that use the property of quantum physics. So whatever that wave particle duality and entanglement and stuff, all of them, they use these properties to store data and perform computations. Okay. And as I kept on saying, this can be extremely advantageous in certain tasks. Okay, for example, cryptography tasks, right? Or for timekeeping sort of tasks. Okay, so it can be extremely beneficial in certain tasks, and they can outperform our normal classical computers, supercomputers even. Okay. And but in certain tasks, our normal computers will perform much better than quantum, because that situation and that circumstance is not a classic case study for a quantum use case, right? And now classical computers, okay, which are our smartphones and laptops, right? So they encode binary bits, right? So the zeros or ones. In quantum computer, it is a qubit, right? Quantum bit or qubit, which we call as a qubit. Okay, so qubit, as I was saying, they are what we saw, the Hilbert space representation, right? So it's not a zero or one. So it can be it is actually the information of an electron at one point of time, such that it stores the state and other information. Okay, so spin or orientation and those sort of things. Okay, and these systems can be many different arrangements all at once. Okay, so which means, like I was saying, that electron can be a wave and particle at the same time. Okay, because of which this property is called as quantum superposition. So this is one of the important concepts of quantum computing, and this is how superposition, entanglement, and what is this? Yeah, and this wave particle duality. All these principles are also we see in the machine learning libraries, which we are going to use for our Azure Quantum examples as well, right? So because, as I was saying, that electron can be in place A and place B all at the same time because of the wave particle duality. That's why this property, because you can never be sure, like what is the state right now? Is it here? Is it here? Is it together at the same place and stuff like that? Okay, so this property, this arrangement which we can have, is called as superposition. Okay, and these qubits, okay, the qubits which we are talking of, they are uh, linked together, which is called as quantum entanglement. Okay, so which means the qubits can represent different things simultaneously. So superposition was one thing, like it can be many things all at once. Okay, and then one thing can represent different. One formula can represent different things. So series of qubits can represent different things simultaneously. Same thing because of the wave particle duality, right? So this is called as entanglement. And now the superposition, entanglement, all these principles are basically exploited by the quantum circuits, okay, the quantum registers which are used in the quantum computers. And then that is how they are solving problems for cryptography, or for a very accurate atomic microscopes or atomic clocks very accurately. Okay, now one of the things which we need to understand is, because of all this is at the subatomic particle level, right? So that's why the quantum computers are very sensitive. So any minor disturbances in the heat, electromagnetic fields, is going to change the orientation of the electrons, right? So it is going to cause some disturbance in the state of the electrons, and then that can easily cause a particle to lose its value at that particular time. Okay, and they are very highly sensitive to all these disturbances, we will term as noise, right? So all these noise, they are highly sensitive to that, and they can quickly what you can say, they can quickly delve into decoherence. Okay, so the information is no longer coherent. So I have started to solve a problem. I have given a wave function to predict the state of the electrons, and I have applied the all the principles of superposition and entanglement and stuff like that. And suddenly there are external disturbances. Okay, and then it can cause the electrons to lose their spin and cause collisions, and basically they descend into decoherence. Okay, so this is process of disturbance is known as decoherence, and then it is very quick, like I mean within like blink of an eye, all the information can be garbled. Okay, so because that is how sensitive, because it's a wave, you imagine that. So any sort of a disturbance to its field, or because it's an electron, so electromagnetic influences and all are going to cause a lot of disturbance and garble the information. Okay, so when we look at the four principles here, okay, superposition, entanglement, interference, and decoherence. So superposition is the ability of the quantum system to be in multiple states simultaneously, which is what, when we are talking of flipping a coin, before it lands as either a head or a tail, in between it can be both head and tail, which is why, I said that it resonates with the Schrodinger's cat principle. So if you don't know about Schrodinger's cat, so Schrodinger said that, if I had a cat which is inside a box which is inside the trunk of my car, right? And then if I'm driving, then at any given point of time, it is uncertain whether that cat is dead or alive. It could be both. So it could be dead, alive. It could be both. So this is same thing. Like it could be AB, it could be BA, it could be 0, 1, it could be 1, 1 simultaneously, because of the way in which electrons behave at the particle level. Okay. So entanglement is taking objects and connecting them by permanently entangling them together. Okay. So when adding an additional qubit to a quantum computer, as I was saying, so let's say if I have 8-bit quantum computer, my probabilities of the computational probabilities are 2 raised to 8, right? So the same way, like when you talk of a 50-bit, the probabilities are 2 raised to 50. The increase in power, the exponential increase in power plus the entanglement of qubits, it allows the quantum computers to solve problems efficiently, finding solutions which are way faster, okay, and with way fewer calculations. Now, when you talk of entanglement, okay, entanglement is something like, a function. So let's say I have something here, like X here, okay. Entanglement is something like, what will happen to Y and how they are interlinked. Entanglement is something like interlinking of two happenings, okay, by some way of explanation, due to which there was there was a belief that, for example, in the universe there could be a probability that, electrons which are far away, electrons which are like totally away from each other, particles which are located far away from each other can share excuse me, just hold on. Particles which are like far away from each other in the galaxy at different zones altogether can still share information because of, as a result of quantum entanglement. Okay, so all this is very hard to even comprehend. I'm pretty sure, so because I had a hard time too, I still am having a hard time trying to explain these things, right? But that is what the behavior of particles at the micro level is, right? Interference, as we said, that they are very sensitive, and coherence is uh, coherence, decoherence is they are losing their spin and their positions and their wave functions by the virtue of the noise which is there, right? Now interference can also be used in a constructive way, so like as a catalyst to amplify the signals, right, and reach your state earlier, so reach your end result earlier than and also it could be also used as a catalyst to cancel signals that are going to lead to the wrong answer. So in machine learning paradigms, when you are having tree based algorithms, right, so when interference can be used as a catalyst to prune away the wrong paths which are going to lead to a wrong conclusion or misclassifications, stuff like that, right? So these are the four pillars on which your quantum computing basics are, paradigms are based on, right? Superposition, entanglement is like function in which I connect two variables at different places and the way they share information. Okay, interference, and coherence decoherence. Okay, so these are the four principles on which our modern quantum computing algorithms are based upon. Okay, so now when you look at the visualization of a qubit, right? Again, this is a two-dimensional visualization, because if you look at the Hilbert space, my 3D vision is not going to be able to comprehend it, and to put it on a paper in a two-dimension space is again, a Herculean task. So what we call it as a block sphere, BLOCH. A block sphere is how you visualize a qubit, right? So qubit is basically, again, as I was saying, it is a wave function. So it's a complex wave function at any given point of time. And this is how you visualize it. So again, they have given you X, Y, Z dimensions, and this is the vector, right? The state vector, and the particle function, the wave function at any given point of time. Okay, so this is the visualization of a qubit. If you frankly ask me to explain the waves and what are the red lines and how are these curves, to just imagine that in a two-dimensional or three-dimensional space itself is like, blows my mind totally. So yeah, I mean, hats off to Microsoft and IBM and all the others who are putting in efforts to build the quantum libraries, make it available to us, and make it available as real life applications. All right. Now, when you go inside a quantum computer, okay, so inside a quantum computer, like a normal computer, you just extrapolate those paradigms and put it into a quantum world. So, in our classical computers, you have registers, you have gates, you have states, right? I mean, states meaning like the state of information. Like for example, when you're building a system, then you have state diagram, right? So if it is a switch like on off, then the state is on, what will happen, state is off, what will happen, when it is between something, what will happen. So those type of states. So same way, you have quantum registers, you have quantum gates, and you have quantum states. So quantum states, there are two basic states of entanglement which are there. Okay, they are given to you by Bell's theorem. Okay, two basic states of entanglement. I've embedded link for us to be able to read into Bell's theorem, because all of these, Grove's algorithm and Bell's theorem and entanglement and all are totally huge separate topics, which in the interest of time and in the interest of technology, it's a separate subject altogether. All right. So I have embedded links if you want to have a read on them, or maybe, if we can have future sessions on these particular specifics, we can see if we can have them, right? So when we talk of real world applications, as I was saying, quantum physics, they defy the common sense notions of causality, locality, and realism. Okay, so in my normal world, so in my normal day-to-day life, even I know that if I cannot see the moon still exists, right? So I know that in the morning, even if I cannot see the moon, or if even if I'm not looking at the moon is still going to exist, right? And I know that a cause and effect relationship will tell me that if I flick on a light switch, I immediately the bulb will illuminate, right? So which means electricity will rush on, it will heat up the tungsten filament, and the bulb will glow. All right. So, but these principles, they are totally go for a toss in the quantum realm. Okay, and then this is what I was talking of. Like at once, the particles on opposite side of the universe could be linked by certain function. Okay, and they are so linked that, let's say, if a particle at one end of the universe changes its position, or changes its spin, the particle at the other end of the universe will be affected, and it might behave in a specific way depending on the function which is linking them, depending on the link which is connecting them. This is entanglement. Okay, so the way in which the bits are connected, this is entanglement. And based on this entanglement function, okay, this entanglement proposition, how we are able to transmit information quickly using quantum computing. Okay, so yeah, so Bell's theorem is here to read. I will not extrapolate a bit on it. Okay, and he proved that all these entanglements for particles even at opposite spectrum of the universe also exists, and he proved it, right? So it was a notion which Einstein scoffed at. Like he said that it's impossible that particles share information instantly, which are like separated by light years, millions of light years away, right? But still they could instantly share information, right? So that was something which is scoffed at, but it was conclusively proved, and that is how this entanglement proposition is harnessed for real world applications as well. Okay, so before I move on to the demo of Azure Quantum Workspace and quantum computing, I would like to show you some of the real world applications for quantum computing. All right, so if you look at here, okay, right? So if you look at here, this is a strontium clock which is unveiled by NIST in January, and this is so accurate. This is so accurate that it will keep a time without losing milliseconds, without losing a single millisecond for the next 5 billion years. So just imagine that this is, more than even the Earth could exist in the foreseeable future. So this is how, the level of accuracy of your quantum computation is. Okay, so ultra precise clocks, it can build ultra precise clocks. So these machines are not something which are, your flight of fantasy or some sci-fi fantasy of the future. So these machines are already built, these are operational. All right, so ultra precise clocks is one thing. Okay, and then okay, as I was saying, cryptography, right? So cryptography, now there are sides to it, two sides to your cryptography as well. So let's go to the constructive side. Okay, now given the amount of possibilities, or the what you can say, the amount of entanglements, and because of the superposition and entanglement fundamentals, the amount of states or the amount of possibilities your electrons could be in can be harnessed in cryptography. So imagine that, using this you can make such a robust key, such a robust cryptographic key, that it would be very hard to decipher. So let's say I have, made a key with a certain so normally what happens is, in your classical computing, is like I have a private key, and then I'm encoding it using some of the known algorithms like MD5 or RSA, and all those things, right? And then the receiver side, he has the key, he applies the key to it, and he gets the decoded message. So I encode it using a key, and then the receiver side has the the key. The decoding key with him. He applies the key, decodes the message, deciphers the message, right? So what if a hacker in between, he's able to whatever the amount of complexity for your key you apply, or the cryptographic algorithms you apply, there can be algorithms, or there can be supercomputers that can, by brute force or by optimization techniques, they can still hack into those algorithms, and can decipher all your information in between, right? So that is what we term as hacking. But imagine, because of the sensitivity of these particles, right? So if, even if I try to, some hacker tries to sort of hack the key, because of the disturbances in the environment of that electron, the spin and the position and the wave function and all, even small disturbance, someone trying to hack it, the algorithm will be able to decipher. The receiver will be able to notice that, hey, there is some change in the, the key, and then he'll be able to know that my information is compromised, right? So that is one way in which you can, use it constructively. Okay, other end, like other probability is, if you're trying to, try to snoop on somebody. So because of the way in which, these algorithms are so fast, they can break the most strongest encryption algorithm, okay, cryptography algorithm, and then compromise your information, right? So just imagine, like, the amount of possibilities. So you can have a very robust key, which will, if your normal algorithms, if they try to even decipher, they will take like normal computers, if they try to hack and they try to decipher, it will take like millions of years, or because of the sensitivity of the the interference and the coherence patterns, fundamentals of the electrons, it can be something like, you can easily understand, because of the, they will lose their coherence, and then the receiver will be able to understand that the information was compromised. So all of these things, right? So could be, it's a double-edged sword. Used constructively, it can be used to have a very robust cryptography algorithm which cannot be hacked into, other way around, if used constructively, I mean, if you are going using it with the malicious intent, it will be able to sort of hack into any of your strongest encryption algorithms and compromise your information easily. So as it is now, that increasing a speculation around AI and all these social media sites and platforms harnessing information, snooping information, cookies, stealing our information, and so that's why we all have all these ethical and responsible AI frameworks and patterns in place, and so on and so forth, right? So with all of these information explosion everywhere, so just imagine the destructive possibilities which these quantum computing algorithms could have, right? So we are not going into the sort of Skynet sort of an eventuality here. So we will still look at the constructive approaches, right? So we looked at atomic clocks, the strontium clock, which can keep time, accurate time, without losing a millisecond for the next 5 billion years, right? And that is how you can sync time, right? You can sync time universally also. So atomic clocks, they are used for that. You can have uncrackable codes, all right, right? And you can have super powerful computers, which goes without saying, because of the exponential powers. Like 8 electrons can have 2 raised to 8, 8 bits can have 2 raised to 8 possibilities, 10 bits can have 2 raised to 10 possibilities. So just imagine, addition of one bit is going to exponentially increase your computing power. So it's like raised to, it's exponential, raised to 2 directly, right? So raised to the bit, so n 2 raised to n will become 2 raised to n plus 1 with the addition of one bit. Okay, so this super powerful computer, so this, if you see, so this q, if you try to list out, this was done by what you can say, an engraving which was to the scale of, I think, nanometers. So it that machine, that quantum machine, that was able to write a q on a nanometer chip, like, not even nano, it is lesser than a nanometer. So 800 U meter. I'm not sure what is UM is. Okay, so yeah, sorry, nanometer. I'm right. So it was able to write that Q on a 800 nanometer chip. So just imagine, like, it was not even visible to a microscopic eye, but the quantum microscope, the quantum machine, the quantum arm of that machine was able to engrave a Q on a 800 nanometer cube, chip, and then it was able to, you were able to visualize it. So you were able to kind of magnify it, amplify it, and see the actual letter here. Okay, so just imagine that, the amount of accuracy and the amount of minusculity and the amount of steadiness the robotic arm has to engrave that q here on that small piece of chip. Okay, so this is the accuracy of quantum computing as well. So improved microscopes, of course, right? Okay, and lot of other things. So it could be used in computer vision in the future. It could be used, of course, in the use of, in the field of cryptography, right? It could be used in the field of microbiology, correct, right? So observing the, behavior of microorganisms, predicting the behavior, how what they will do, like, x plus one point of time and stuff like that. All right. So yeah, so immense possibilities, but then there are, certain problems which, of course, still our classical computers will be able to solve much better, and maybe quantum computers maybe never be able to deal with those realms in which our physical classical computers work upon, right? So yeah, having said that, let's quickly jump to the Azure computing demo. Okay, so when you look at the Azure environment, uh, this is my portal. Okay, in my portal, I'm going to show you. When you go here, I go home, I create a resource, right? And when I create a resource, I can search on quantum here, Azure Quantum. Okay, so Azure, right, Azure Quantum, and then it will give me this Azure Quantum. So earlier it was in preview, now I think it is already GA. Okay, and then you choose your resource group and stuff. So maybe I'll select my existing resource group, I'll give some name here, account, I just get some storage account. Okay, I click next, and then these are the providers which I am able to choose. So you have Honeywell Quantum Solutions, you have EonQ providers, right? So basically, if you look at all these providers, they are the ones, I mean, they are the libraries, or they are the what you can say, platforms which are going to provide us the manipulations. Like, when you look at those entanglement, and you look at those what is this, superposition, right? So they are the ones who are going to provide us the infra and the basis for the libraries for doing these calculations or computations, right? So you have Honeywell Quantum, you have Eon Quantum, and by default, if you don't choose anything, Microsoft QIO is anyways added, right? So it is anyway added to your quantum workspace, and then you create the quantum workspace. Once you create the quantum workspace, let's go back to the resource which we already created. So I go back. So this is my quantum, okay, right? And then you have different ways of doing it, right? So you can either you can download a QDK, which is a quantum development kit, right? So you can install a QDK and start using it in your Visual Studio, right? So you once you install your QDK quantum development kit, then when I click on a new, so let's say new project, okay, I can get a Q sharp application here, right? I can give a Q sharp application. So Q sharp Honeywell Q sharp Eon Q console application, or just a normal Q sharp application. So I'll just search for Q sharp, right? And yeah, this one, see, Q sharp application, right? So when you just make a what you can say, you make a Q sharp application without specifying any template, Honeywell or Eon Q, it will use the Microsoft QIO, the one which we saw, which was inbuilt there, right? So now I just click next, or maybe, yeah, I click next, and I give some app name to it, saying test, whatever, yeah, right? And I create. I will just quickly walk you through the the Q sharp paradigm. Okay. So once you just create a empty application, it will by default create a console application with a message which is called as Hello Quantum World. Okay. Now, if you look at this, it is pretty similar to our C sharp paradigm, right? So you have a namespace which is quantum, which is your C sharp namespace, and these are your using libraries, right? So this is open Microsoft Quantum Canon, Microsoft Quantum Intrinsic. Entry point is your main function, right? And then you have operations. So if you know the world of functional programming, you will have operations and variables which are passed as states between those operations, correct? So same way, so you will have your entry point, which is your main, and you will have some operations which you are doing. So it's a very, very simple very simple algorithm, I mean, not algorithm, very simple program here, just to get you started. But don't be too much hustled about the syntax, right? So it's very similar to your C sharp one. And also, if you go back to your Microsoft website here, I like to show you. Okay, so here you have all the samples which are, yeah, so you have samples which are also in Python, in C sharp, and in Q sharp. Okay, so if I were to show you here, okay, yeah, so this is the Q sharp code, right? So the one which I'm showing you is the Q sharp code. You can also write this in C sharp, so using your own C sharp language, but with the quantum machine libraries. So this is a Q sharp application, right? And the other application which I'm going to show you, so let's say file, open project solution. Okay, I go to OneDrive, repos, quantum, no, sorry, repos, just just hold on, cancel, and I will go file, open project. Okay, just let me close it and open a new Visual Studio application, because I am not able to locate my, right. So yeah, so let me open my Q sharp demo solution here, right? I want to walk you through a little set of operations here. Just give me a second till it opens. Yeah, so this is a Q sharp demo, right? So Q sharp to generate a random number, right? To like a real random number. So between 0 to 50, every time I run the application, it will just throw a random number at me, right? Okay, so sampling a random number between 0 and maximum. So maximum is 50. You can give it like, let's say, let me give it something like this. Maybe I'm not sure, if it will able to compute, but yeah. So let's say that, right? It was integer only, so maybe let us make it double. Okay. I'll have to change a lot of things. It will be right. Okay. So yeah. Right. So just I will be uploading the GitHub for this. Okay. Vishwas, you later on I'll give you all the resources. You can upload it. All right. So share
Sure.
the GitHub for this, and in the GitHub I will show you that how it will be operating. Right. You can play around with the integer values, and you can give a really long number and see like the amount of time it is able to generate that computation in. Okay. So now, as I was saying, so namespace is your normal C sharp namespace which you have. These are the libraries which you are going to use. So dependencies here are your frameworks, which is you will need a .NET 3.1 plus framework, right? And I have the QML, which is the quantum machine learning library installed here. So if I go to tools and you get packages, I will okay, so when you're doing the machine learning example, you will need the quantum machine learning library. So this is just a simple quantum random number generator. So for that, the only requirement is your QDK, quantum development kit, you need to download, and the 3.1 .NET core framework. All right, so this is your namespace. This is all your using libraries. Okay. And then this is your entry point, which is your main function. What is your main function doing? It is going to call the sample random number in range function, right? And the sample random number in range function, what it is going to do is it is going to generate it is going to generate certain bits. So if you see, like, for example, this is how your functional programming works, right? So you have information passing through different series of operations, and thus they are mutable. This is right. So when you see, like, when you just start off a quantum calculation, okay, so you have something called as a qubit initialization. So initialization here, you will always be initialized to 0. So when you say use q equals to qubit, so when you are defining a variable here, so this is our a qubit variable. So use q, so this is like var x, right? So var x, you are initializing it. So you are using qubit, initializing it. So initial is always 0. Okay. When you have h of q, okay, so this h is a variable. H is a function which is now putting this variable into a superposition, right? So which is like here, uh, when I say h of q, it can be probably, it can be like a point 0 or a point 1. So it can be like at destination a or destination b, going back to our superposition principle, right? So we are, h of q will be your superposition. Okay, so I'm allocating it a superposition so that it has 50% chance of being either 0 or a 1, right? And then when I do m reset z of q, so this m function is now the measure function. So h is putting it into a state of superposition, and m is now giving me the value. So now measure the value and return me the value at that whatever particular point of time. So my program, when it is trying to sample the numbers between 0 and 50 or 0 and 150 at certain instance of time, when it is going to return me that number, this is that instance where now I'm saying that, okay, now you are in a state of superposition. Now stop, and at this point of time you can return me the value. What is the measurement of this particular qubit value at this point of time? Okay, right? So let us just run this demo. I'll just run it. Should I have run it without building? right? So now it is sampling a random number between 0 and 150, and it gave me back a number 36. Run this n number of times, you will come across. Like last time when I run it, I got a number 28, so now I got 36. It could be anything. Play around with the values, make it exponentially larger. Look at the time in which it returns you back the result, right? So yeah, so these are some very basic computations, right? So this is not even scratching the surface of what Q sharp library or QDK and all these are all about, right? So just understand that, don't be too much get overwhelmed by the syntax and all. It's not much, so it's like your namespace, and you can anyways do it using C sharp. So if the C sharp code, if I were to show you, so let me open. So file, open, solution, and let us go to your quantum samples, machine learning, and yeah, I will open the machine learning solution here. So I'll be sharing this GitHub. This is a Microsoft GitHub only. So this is not something which I concocted. So I'm building my Q Sharp code on top of these code samples which are shared by Microsoft for machine learning, right? So you see the GitHub of Microsoft here. They have a lot of, so this GitHub, right? So they have a lot of samples here for quantum. They have chemistry, diagnostics, interoperability, machine learning. Lot of things, right? So I was in the machine learning here. Inside machine learning, you have half moons, parallel half moons, and mine samples. So I will be discussing the half moon sample here. So what is a half moon sample? Half moon sample is nothing but it is a classification problem. Classification problem, which means given a set of training data, I'm training it on a half moon data set. What is a half moon data set? A half moon data set looks something like this. Okay. Let me go here and show you. Right. So half moon data set is nothing but a data set which has been trained on labeled data, okay, to cluster points between a set of two half moons. Okay. So I'll just show you how it looks like this, right? So basically, you are training an algorithm to, label data on 2 points here, like points clustered on this and this. So these are the half moon data sets. Okay. So this is a classic, classification problem, right? And then on some test data set, you have to predict whether the point is here or here accurately, and then depending on your true positives, true negatives, false positives, false negatives, you will be coming up with the accuracy, right? So this is the classification problem which we will be solving with our Q sharp, right? So machine learning, right? So here, now the previous one you saw was uh, yeah. So the previous problem which you saw was with Q sharp, right? So it was Q sharp. Now this is C sharp using quantum machine learning library. So now you see this is our classic C sharp syntax, right? So you're using, and I'm using the quantum Microsoft quantum machine learning library from where I'm getting the simulators, right? And this is your entry point, which is your main. Okay, so we are loading the data, which is the JSON data is nothing but, if I show you the JSON data, right? So this is the data your JSON, which is nothing but the training data and the features. Features are the coordinates of the point in the half moon circle database, right? So half moon circle data set which you saw that. So here these are the labels. So features, these are the features, and these are the labels, right? So labels are like, features are the coordinates, and the labels are like whether it is belonging to the bottom part or the second part, like, okay, so in part A or part B, right? So these are the, yeah, see, these are the labels. Labels is 0 and 1, which is belonging to the upper half moon or the lower half moon. That is the labels, and these are the features, which are the what you can say, coordinates, right? Okay, so this is the training data and this is the validation data, which means on this is an unseen set of data on which I'm going to validate my result and then predict it if it is putting it in the correct classification bucket or not. So it is putting it correctly in the upper half moon or the lower half moon, right? So this is what I want to test. So this is my JSON data, right? This is my host file which is in C sharp. Okay, so I'm loading the data and we then define the classifier parameters we want to start our training iterations from. So for a classification problem, normally, we will use LGD, linear gradient descent, right? Algorithm to do that. Okay. So now we will initialize our vector simulator as our target. So what sort of target we want? So we want a target machine as a quantum simulator. Okay, and then these are the half moon model. If you look at that, yeah. So this is our half moon model is from our q sharp file. So this is our training q sharp file. So this was our host file in which we are invoking the q sharp file now. So our quantum learning algorithm file, right? So where we are going to have the uh, code for our training, right? So this is classifying using the what you can say, the quantum computation syntax, right? So for these all these things, right? First of all, we need to understand the features and labels and classifier structure in terms of normal machine learning, and then we will be able to process the Q sharp syntax. So no worries, all these things, right? Are very very cleanly and nicely explained. So what is learning rate, mini batch size? So these are nothing but these are the classic tenets of your classification problem in machine learning, right? So machine learning universe, where you will have the learning rate. So what is the rate at which your algorithm is learning? The epochs, the number of epochs of iterations in which it should be running. The batch size, the tolerance level. So all these are the parameters, hyper parameters which we are setting for our machine learning. So these parameters, which are the parameters, right? So number of epochs to run to train the model, and then you're going to actually infer the model, right? So from the validation data set, right? So yeah, so we'll discuss this at length in future sessions, where we will go down to each of the syntax level and see how it is introducing the h value, how it is introducing the measure value, and at what point of time it is going to return us the calculations, right? So just let us run this data set, okay, and just see that how quickly it will return me back. So it will just train also, it will try running this normal in the normal Azure machine learning workspace, see the amount of time it is going to train and infer your validation data set, and you compare the amount of time it is going to run in the quantum machine learning, right? So I'm just going to run it here. Let's say, yeah. Okay, I'm going to run it, and then you will see that because the validation data set is already there in our JSON file, right? So just look at how quickly it will give you that XYZ classifications were wrongly classified, and so training and testing, everything is happening like at unimaginable speed. So still I'm operating on a limited capacity CPU computer. Imagine if you run it on a GPU, how fast it would be. And GPU on a classic AML Azure Machine Learning Studio workspace vis-a-vis the quantum machine learning workspace, you can compare and contrast. And I'm very sure you would be like totally, yeah. So just it is running for so many epochs, huh? Like just look at the number of epochs it is running, and you try to train it with your classic Python libraries or your Azure Machine Learning works studio. Try training it and look at the amount of time, right? And you're using gradient descent, right? So you're using the LGD, linear gradient descent algorithm for that. You look at the time complexity there, the accuracy of course that won't differ, but just look at the what you can say, the amount of time taken for the computation to return you the results, and here every time you train and test, right? And then yeah, of course, with quantum machine learning library, the results will be infinitely faster, exponentially faster. All right, so it is training, right? It is training all the samples, the half moon data set, and then it will run the model, the classification model on our validation data set, and I will tell us how many classifications were incorrectly classified, or how many of them were correctly classified, and stuff like that. Okay, accuracies also will be pretty high, pretty high. So in our normal machine learning terminology, accuracy of like 85% is already like touching the sky. So here, like we were saying, like atomic clocks, right? They will be predicting correct time without losing a millisecond. So now here, observed. This is like, it has begin. It has finished training, and then with this estimating training complete, find optimal parameters, and then observed 13.33% misclassification. So from the validation data set, about 13.33% were misclassified. So they are actually zero but classified as one. So they belong to the upper moon, and they classified in the lower part of the moon and stuff like that. Okay, so they were misclassified. And yeah, so this is within a matter of I think couple of minutes, not even couple of minutes, like 1 minute, some 10 seconds or so, we got our calculation back. Try with a bigger data source, and I'm sure the speeds would still be unmatchable. All right. So yeah, having said that, let us go back. Okay, right. So yeah, so this is what so few of the real world implications and applications we saw okay, let me swap the view. Right. So these were few of the real world applications we saw, and this is not something which we are forecasting will happen. They're already there, already being built, and companies are touting it and like the I mean it is like the technology of the future for sure, right? Something to watch out for. And yeah, so this is how we saw like what quantum computing can do for us, and our journey into the quantum computing. So just like not journey, I would say just an introduction to the world of quantum computing. So yeah, I with that I conclude, and I hope that you find this as fascinating as I did when I initially started off. And yeah, so I hope that you would be as interested to explore the world of quantum computing, Azure Quantum libraries, Q Sharp, and the probabilities with which it can tackle all the machine learning, classic machine learning, or quantum machine learning problems. Right. So all the best for that, and with that I conclude my session. So Vishwas, over to you.
Yes, ma'am. Thank you so much for such an amazing session on quantum computing. There are some doubts from the participants. I think we can take some Q&A and we can
Sure,
complete it.
sure, absolutely. So just let me go to the screen. I think I stopped sharing my screen, but it should be
Yeah,
okay.
yeah.
Yeah.
So greetings, Priyanka. Quantum leap activated. You got this. I think Ranganathan Halin Sami. Yeah. Thank you so much, sir. Thank you so much. And particles away from each other, no matter what is the difference in the distance having the state. Uh, he's asking about all the things about the current cryptographic, and he's also asking about the infrastructure and the library, how to start with any of the things like that. That's what he's asking about.
I'm not able to see the question correctly. So can you reword it for me?
Yeah, he's asking about no matter what.
Particles away from each other, no matter what is the difference in distance, having the same state. Yeah. So I think that's it's
He's I think he's probably referring to this.
yeah, correctly. I mean, it's just an observation. Like particles away from each other, no matter what is the difference in distance, can have the same state, right?
Yeah.
Right. Correct. Yeah.
And he's asking, ma'am, say about quantum realm.
What you want to know about quantum realm? You tell me that. So because see, when I talk of when I talk of all these quantum libraries which are made available, so not even gotten close to the IBM offerings or the Google offerings, right? So these are the Microsoft offerings which we know. This is Honeywell and IonQ and all these libraries, right? So if you want if you want me to talk about quantum realm in the terms of physics or mathematics, then it would be very hard for me to explain. When you talk of quantum realm, right? Quantum realm, like the position of the particles, or how the particles are moving, or the wave functions in which you're going to define the particle, or how you're going to posit the particles, or posit a function when trying to define the movement of the particles, or posit a wave function trying to predict something, some possibilities. So this is what I can say. But again, as I said that I've been very new to this field as well. So as maybe just 2 or 3 workshops with Microsoft training on Azure Quantum, right? So be specific when you say about quantum realm. I am not sure what would you want me to talk about. Yeah,
Yeah.
and again, to Ranga's comment, right? Current cryptography algorithms at risk, so quantum proof algorithms are being developed. Yes, absolutely, right. So, which is what I was saying, right? There are two sides of the coin. So, cryptography, you can have algorithms which are hack proof if you build them using quantum algorithms, right? Quantum circuits. Otherwise, you can have, like, you can use them to hack into very robust algorithms. And so yeah, that's why, correct. So it's two-way. If algorithms at risk, so quantum proof algorithms are being developed. Absolutely.
Yeah, and he's also talking about infra hardware platform libraries as well as simulator based providers.
Yes, correct. So if you look at, just let me again, go back to the Microsoft uh, documentation. Okay. So there, when you go, there are simulators and targets which you need to define, right? And then there are a lot of rules governing that. Like sometimes you cannot have, for a target you need to have a result and stuff like that, right? So yeah, I will just paste a link for people who are interested in delving deep into like, at least what you can say. Yeah. So when you are talking of targets in Azure Quantum, so you have optimization solvers, you have quantum devices, and you have quantum processing units, QPU, right? So in QPU, you have a basic measurement, feedback, no control flow, right? So all these things. So I'm just going to paste this in the chat window. Maybe Vishwas, you can pass it on to people who are interested. All right.
Sure, ma'am.
Yeah. Correct. So this is the Azure Quantum in documentation, Microsoft Azure Quantum documentation, right? So yeah,
Yeah.
this is all the information which you have here, the libraries, the code samples, the quick starts using Python, using C sharp, using Q sharp, and more. Yeah. So
And yeah, I think 11th is asking about with Pi, how, ma'am? Like,
yes,
because,
Python also. Yeah, has. Just go through the documentation, right?
yeah, you took an example from your slides. Yeah.
Yeah, you can. So same a classification problem you can do with Python as well, right? So I can you go to this page, and you have 3 options, as I said. Like, can have Python, you can have Q sharp, you can have C sharp. All right. So yeah, same example. There are code snippets also to do it with Python. How to do it with Python? How to do it using Python libraries? Yes, absolutely. You can do that same thing with the I think quantum learning studio also, right? So it's
Hmm.
not I mean, sorry, not quantum learning studio. You can for example, okay, let me share my screen once again, okay, to answer Lavan's question. Okay, so let me share my screen once. Share screen. Share.
Yes,
And I
ma'am.
was showing you the GitHub, right? I was showing you the GitHub here. Sorry, where is that? I just now opened it, right? Okay, sorry. Yeah, here. If you go to Q Sharp libraries, using Q Sharp. So actually you will find it, yeah, Python SDK. See, you get here, see, Python SDK. So you can use the tutorials here and the Python SDK here to solve the same problem we are solving with the use of Python libraries. Absolutely, you can do that, no issues, no problem at all.
Sure. I think no questions. Do if you guys do have any questions, drop it down in the comment section below so that we can take some questions from here. So yeah, I think Ranga sir was actually was parroting Priyanka to support her content discussion, which is
Correct.
okay.
So actually, I happen to know, Ranga. He's also an active contributor in the space of quantum computing. So
Mm-hmm.
he's also done some amazing sessions on quantum computing as well, and he's also done the developer courses of Azure Quantum. So yeah, I mean actually, yeah, I mean Ranga, you are also one of the authorities on on quantum computing.
Yeah, I think if you are free, you can connect with me on LinkedIn, sir, or else I'll connect with you on LinkedIn so you can give me a session on our community. I think, yeah, Lavant is saying, actually, I'm really fascinated about quantum computing, ma'am. I've done some basics presentation in my engineering classes, but I could not proceed further, like whatever, to find out the resources or how to start journey in quantum computing. That's his question.
Right, correct, right. So that's what I said, right. So identify provider, the platform which you are interested in. So many people, they start with the IBM. Google, I think, is locked its door for quantum. It's not really available like the Azure Quantum, so till few months back, Azure Quantum was the preview. Now it's gone GA, I think, right. Yeah, so choose your platform, choose your cloud provider, choose your choice of computing. So if you go to IBM, I think it is QI disk,
Qiskit.
something like that. Yeah, yes,
Qiskit.
Qiskit, yes, Qiskit, right. So IBM.
And there
So
is Silk. There are other frameworks. There are other
correct,
languages
correct.
apart from Q Sharp. You guys can start working on it.
Yeah, right. So yeah, so just
Or else,
choose
if you are
your
too free, you can go to Numba, create your own library, and start working on it.
yeah, correct. Yeah, true. Create your own data sets. Can
Yeah, that can
possible.
be done. That can be done.
Yes,
I
can be
think,
done.
guys, this is the end of the session. Thank you so much. And meet you guys on the next sessions that are coming up. And hopefully, you guys stay jacked up for getting more knowledge from us. So, thank you so much, folks. Thank you so much. Bye. Thank
Yeah,
you.
thank you, Vishwas. Have a nice day, and all the best for your future sessions. And meet you soon in August for our AI series.
Yes, ma'am. All right. In the
All right,
meeting.
thank you so much.